The episode discusses the illusion of time and explores the concept of time in the universe. It questions whether time is fundamental and explains the synchronization of time.
Hey shortwavers, Regina Barber here. So, our world seems like it's designed to help us stay on time. It's right there on all of our devices.
And you could still call a phone number if you want to. I mean, I don't know if you remember, Gina, but that was the way we used to get the time.
I actually do, like barely. I remember calling maybe once in my childhood.
Eastern Standard Time, 13 hours, 54 minutes.
And yet, even though it's easy to tell what time it is, it's not so easy to tell what time actually is. Which is where NPR science correspondent Jeff Brumfield comes in.
Yeah, that's right. I've been on a bit of a quest to figure out the truth about time, and I'm here to tell you that it's far more flexible than I realized. And some scientists think it might not even be real. Time might not be fundamental.
This has been going on for like decades, that there have been these hints coming up that space and time aren't fundamental properties of the universe. And they're just not telling anyone about it.
Wait, what? I don't know what to believe anymore if space and time aren't fundamental properties of the universe.
Yes.
But today, Jeff, you're going to help us. Today, we revisit your time episode and ask, where does the time we use in our daily lives come from?
How is it different from true time in the universe?
And if time isn't a thing that makes the universe tick, what is? You're listening to Shortwave, the science podcast from NPR. Okay, so Jeff, we're here to talk about time, and maybe the best thing to do is to start off with the time we interact with every day. Like, I can see the time on my phone, and it's probably synced up to the time on your phone, so that we're all on the same page. Like, how does that even work?
Yeah, I mean, we've never been more synchronized, and I wanted to figure out how that was happening. So to sort of learn about the time we see in our daily lives, I headed out to Boulder, Colorado to pay a visit to the National Institute of Standards and Technology. And it was really snowy the morning I showed up, so it turned out I was running late.
Turn right onto Raleigh Road.
Well, I'm just arriving and they have a clock out front, and I can see I'm about 7 minutes late. So I rush across the Institute's campus. Sorry, just give me one more sec. And arrived at a lab run by a guy named Jeff Sherman. Hello. Hi. I'm sorry I'm running late.
We only measure the nanoseconds.
I enjoy the time jokes. Okay, so what was it like inside the lab?
It was just this sort of nondescript beige room. There were a lot of wires and computers, but what really stood out were these 3 big gray boxes, each of which held a high-precision atomic clock. This one's called George, Fiona, Elvis?
They all have quirks and personalities, and when they fail at 2 a.m., you want to have a little bit of compassion for them, so you give them names.
I'm actually all for naming machines. I'm all for that.
So to see how one of these atomic clocks actually worked, we went over to the one called Elvis.
And the interesting bit is if you lean down and look that way, you should see a pink glow through a little hole.
Oh, yeah. So that glow was coming from atoms of hydrogen. And here's how the atomic clock works. You excite the hydrogen, and then that hydrogen loses its energy by putting out light at a very specific frequency. Sherman says you need to think about it kind of like striking an atomic tuning fork.
Okay, so like a regular tuning fork, you strike it, it gives off a specific frequency, and then you can tune your piano or guitar or whatever to match that tune.
Exactly. You match the note. And this contraption works the same way, except it's using a note, a tone, a frequency of light instead of sound. And so what you're tuning is an electronic clock circuit that's then used to keep track of the time. There are 21 clocks like Elvis spread across the campus, and they're all used together to set America's time. It's this amazing system that's accurate to better than a trillionth of a second.
Wow, that's wild.
It's really a remarkable system. But here's the thing. There's this sort of catch-22 to the whole setup. Because if you stop counting all these little trillionth seconds, if you skip them, if you blink, if you miss one, you don't know what time it is anymore.
In exchange for this wonderful idea, you're now beholden to count forever and not lose track.
This feels like the most Sisyphean job, the most sort of like rolling the ball up the hill forever and ever job I've ever heard.
You said it, brother.
So if you stop counting, time stops running.
I mean, basically, yeah, that's kind of what happens.
Wow. Okay. So these clocks are just counting forever, and we just sync all of our gadgets to them?
I mean, that's what the U.S. government will tell you time is for sure. But here's the thing. When you take a step back from that version of time and look at time with a capital T, the truth becomes a lot more messy.
A lot of us grow up being fed the idea of time as absolute.
So I spoke to a theoretical physicist named Chanda Prescott Weinstein, and she is at the University of New Hampshire. She says she thinks this absolute ticking time is only what the government wants you to think time is. It's not real time. And the reason they want you to think this, Gina, is because it keeps us all in line.
I love where this is going.
Well, think about it, right? The official time runs our lives. It says when planes take off and land.
When does the market open? When does the market close? Can I make that trade right now?
Are my kids at school on time? Am I late to work? This is about the economy, Gina.
Oof.
Yeah, capitalism sucks. And I think a lot of people's relationship to why time is not cool is structured by the resource pressures that we feel.
We're punching the clock. We're running late.
Yeah.
I mean, I get it. But if this stuff is partially a cultural thing, what's underneath it? What is time?
Well, as a physicist, you know that this all comes back to Einstein and the general theory of relativity and the fact that time and space are tied together. Yep. And it's all part of something Einstein described as space-time. And the key thing to know is space-time can bend. It can curve.
The way to think about it is that curvature is stretching out time.
The thing that stretches time better than anything else is gravity. So the stronger the gravitational field, the slower time flows. And that means that for someone on the surface of the Earth, time is flowing a little bit more slowly than, say, someone at the top of a tall mountain. These effects are very small compared to a human lifespan, but when you start to get further from Earth, time gets really freaky.
Okay.
Another person I spoke to is Katie Mack. She's an astrophysicist at the Perimeter Institute for Theoretical Physics in Canada. And she explained that the universe is expanding from the Big Bang and that expansion is also stretching time.
When you see things in the really, really distant universe, because of the expansion of the universe, it takes longer for things to happen.
And the example she gave me was if you're looking at stars exploding, they're called supernova. And if you compare one that happens near Earth and one that blows up far away,
we see a star exploding, and that star takes about 10 days to go from the sort of brightest part of the explosion to dim again. If we look at it in the very distant universe, it might take 20 or 30 days.
Mm-hmm.
So again, that star isn't exploding more slowly. It's that time, it's literally ticking more slowly, at least from our perspective. When Mac looks at really big events in the universe, like the Big Bang, time becomes so twisted that they don't even really bother with it.
We don't really use time as the marker for the passage of time, if you see what I mean.
It's very similar in astronomy with distance. We really don't use that anymore from so far in the early universe. So
exactly. And in fact, space-time are linked. It's actually aspects of the same problem.
Right. So instead of using the term time during the early universe, what other term or concept are they using?
Well, they focus a lot on the density of the energy right after the Big Bang. The universe was so compressed back then that actually tiny fluctuations in energy would radically shift, how time flows. And so time's ticking in all these different ways, but the energy is a more sort of universal, if you will, marker during the early days of the universe.
Yeah. So it seems like once you get far away from Earth, going back into time in the universe, even defining what time is, it just gets super confusing.
Yeah, I mean, it really does. But then Mac also told me it gets really weird on the subatomic scale. In fact, theoretical physicists who deal with fundamental particles have begun to suspect that maybe space-time isn't the sort of foundation on which the universe is built at all.
It is a little bit maddening because mean, you're just trying to have a conversation. They're like, oh yeah, space and time are probably not real. And you're like, wait, what is then actually?
Okay, so first you tell me space and time aren't fundamental, and now you're telling me it's not even real. So, so what else?
Yeah, right. Where do we go from here if time isn't real? So
yeah,
let me take you down the final level of the rabbit hole, Gina.
Okay.
I tracked down one of the physicists that Katie Mack was talking about, a guy named Nima Arkani Hamed. He works at the Institute for Advanced Study. And for about a decade, he's been pondering all the problems with space-time.
Time plays a really starring role in what I've been thinking about, which is why I thought it would be fun to talk.
And we talked and we talked and we talked. It was well over an hour conversation. It was super fun for me, but also super complicated. But I think maybe I can kind of sum it up now.
Okay.
Basically, it comes down to the collisions inside the world's most powerful particle accelerators. Now, a big part of Nima's job is to calculate what should happen in those collisions, like basically to use math to see what particles come out when particle A collides with particle B. And according to the math, this should be really hard to do. Like it should take thousands and thousands of pages of calculations, but it doesn't work that way at all. It turns out the solution is vastly simpler.
Oh, I'm so excited. Simple.
And when I say vastly simple, I literally mean like tens of thousands of pages compared to one line. Okay, so that's a very strong indication that there's a better way of thinking about things.
And so it's like, it's too good. It doesn't make sense.
Yeah.
So Nima actually thinks time is the problem. Like,
wow.
In normal physics, as you know, time is this great way of keeping track of what's happening when and keeping track of events and making sure everything's in sequence. But in these calculations, he thinks that's actually making things more complicated than they need to be. That if you looked at it without using time, you got rid of time altogether, these collisions would actually make more sense than they do when you're trying to use time.
This would have made my test so much easier. So we just ditch time. We just make things time independent. But what do we replace it with?
Yeah, I mean, it's hard to get your mind around. And the truth is, the reason he's been thinking about this for 10 years is he's not sure. So he's currently playing around with these wild geometric shapes that actually describe the collisions without using time. He showed me how they work. They were really cool. But ultimately, they're just math. There's no real sort of underpinning understanding of what they would mean in terms of the fundamental thing that replaces space and time.
What elements of ultimate reality are, we don't know. We keep getting the carpet pulled out from under our feet.
But I should add that, even Nima wouldn't want to get rid of time altogether. I mean, whatever it is that is more fundamental, it would still have to create some sort of time-like behavior at human scales. Because, of course, time is real. We all know that. Like, we live it every day.
Well, Jeff, funny enough, we are out of time. But I want to thank you for sharing your adventure on the very nature of time itself with us.
Oh, it's been a pleasure. Thank you, Gina.